So it's my pleasure to introduce Anne Moreau from Paris, and she's going to speak about action of automorphism group of the Jacobian of Klein's quartic. Thank you very much.
Yeah, so thank you very much for the invitation, and thank you. I would like to thank the organizers for this beautiful conference. I am very sorry that I could not come in person, and so I thank the organizers for giving me the opportunity to speak online. So in principle, I am working on representation theory, and particularly in the context of vertex algebras. But today I would like to talk about recent joint works with Dimitri Markouchevitch on the action of automorphism group of the Jacobian of Klein's quartic curve. I thought it could be related to the topic of the conference, but I'm sorry in advance that I'm not really an expert on this topic. So let me explain the context. So I consider the Klein quartic curves, which is the curve, the projective, smooth projective curve defined by the following homogeneous equation. And Klein discovered in 1879 that these quartics enjoyed many remarkable properties. So in particular, it is a smooth projective curve of genus 3 with the highest possible order automorphism group for this genus. Indeed, the automorphism group is a so-called Klein's simple group, and this group has the order 168, which is precisely 84 times g minus 1 here, since g is 3, and this is precisely the Hurwitz bound. So this is the highest possible order for such group. And there are several descriptions of this Klein simple group. In particular, it is isomorphic to PSL2 over the field F7, and this is still isomorphic to GL3 over F2. And also, you can notice that this is the second smallest non-abelian simple group after the alternating group A5. All right, so now we are interested in the action of this group on the Jacobian of this curve. So since this group acts on the Klein's curve C, it also acts on this on its Jacobian J. And I recall that this is an abelian variety of dimension 3, the genus of the curve. And this is by definition of a quotient of C3 over the period lattice of the curve. So here C3 stands for the vector space of global global holomorphic differential forms on the curve. And this action leads to a linear action on C3, which leaves invariant the period lattice. So we notice that also plus or minus identity leave invariant the lattice, and now we consider the direct product of H with plus minus 1. And actually, this is a maximal finite group of linear transformations leaving invariant lambda. And this is a group we will be interested in the rest of the talk. So notice that in fact, G is precisely the automorphism group of G as a principally polarized abelian variety. So it means that it preserves the principal polarization on the Jacobian. So our main result is the following. The quotient variety of J by its automorphism group, so this group G that I consider, is a weighted projective space with weight 1, 2, 4, 7. So in particular, it is a complete toric variety, singular complete toric variety. So this is the main result. So let me mention that, let me recall what is a weighted projective space first. So I recall that this is a quotient. So here I give the definition for any weight k0, kn. So this is a quotient space of C n plus 1 minus 0 modulo the C star action, where the C star action is given by the weight K0. It acts diagonally with the weight K0, K1, Kn. So in particular, with the weight 1, 1, 1, you recover the projective space, n-dimensional projective space. And equivalently, you can define the weighted projective space as the proj of the polynomial algebra graded by the Ki. So this means here the degree of Fi are Ki. So in particular, it is known that a weighted a weighted projective space is a complete toric variety, possibly singular. And now I would like to explain some motivations of our result. Actually, our result is motivated, and it also proves the particular cases of a more general conjecture of Bernstein and Schwarzman on complex crystallographic groups acting on a complex vector space. So let me explain this conjecture and explain after why our result is part of this conjecture. So I would like to explain this conjecture. So I would like to start with general remark. If I consider a connected complex algebraic variety and a discrete group, discrete subgroup of the group of automorphism of X, then in many cases, if the W is generated by reflections, so I mean, by reflections, I mean here an element of finite order whose set of fixed points, of fixed pairwise fixed points, is an affine hyperplane, then the quotient has a simple structure. So this is a general philosophy, and a famous example is a result of Chevalley-Sheffard-Todd, is the following situation. Let's consider for X the n-dimensional complex space, and for W a finite group of linear transformation of X. Then it is well known that W is generated by reflection if and only if the quotient space is isomorphic to Cn. So equivalently, the algebra of invariant polynomials is polynomial algebra in n indeterminates. So this was proved by Chevalley for any characteristic, but for W generated by a reflection of order 2, and Sheffard-Todd considers a general case, but over C, if I am correct. So another example, if X is a upper half plane and assumes that X over W is compact, then here we have that W is generated by reflections if and only if the quotient is a projective line. So this suggests that it's usually a simple structure when W is generated by reflection. And Bernstein and Schwarzman consider the following situation. We assume that W is a discrete group of affine transformation of Cn, and they consider the case where W is a complex crystallographic group. And we say that such a group is a complex crystallographic group if its translation subgroup is a full rank lattice, so it's a 2n rank lattice. And equivalently, this condition is that Cn over W is compact. And they formulated a conjecture, which is a kind of analog of Chevalley-Sheffard-Todd result. So it's quite old, it's 1978, and it's still an open conjecture. And the conjecture is that for any irreducible complex crystallographic group, W, generated by reflections, the quotient Cn over W is isomorphic to a weighted projective space. And actually, the converse is also true, but the converse proves that the fact that if the quotient is a weighted projective space, then W is necessarily generated by reflections. So in particular, you see that contrary to the previous examples, here the quotient might be singular. And actually, this is not so surprising because also W is generated by reflection, the stabilizer of some points might not be generated by reflections. And the image in the quotient of such points are singular in the quotient. So here you see the singularity, and in fact weighted projective space are singular as well. All right, so now I would like to explain that this conjecture has been proved in some particular cases. Also, it's still open in full generality. So I would like to first discuss n is equal to 2 case. Any questions so far? All right, so I would like to discuss conjecture in rank 2. So in fact, here the conjecture is essentially proved, but unfortunately we need to keep almost. So the conjecture is proved for almost all irreducible complex crystallographic group generated by reflection. So more precisely, we have the following results by Schwarzman and Tokunaga Yoshida, so in 78 and 1982. Which claims that the quotient of C2 by any irreducible complex crystallographic groups generated by reflection is a weighted projective plan. And here, in fact, they consider only split group. So it means that the group is a semi-direct product of the subgroup of translation and the linear part of the group, which is finite. So let me explain a little bit. So the problem is that there are several problems. So first of all, they consider only split, and some groups, a crystallographic group in Popov classification are non-split. And second problem, unfortunately, a Popov classification is incomplete. And so it missed some group in this theorem. So this was pointed out by Goryunov and Mann more recently. So in fact, Popov classification contains precisely 20 complex irreducible sorry, they are too much complex, crystallographic reflection group for n is equal to 2. And if you consider all this group for the split one, so it's all except 2, the possible weight for the projective plan, you can check, and its only possibilities are this weight. And but actually, recently, Kosia, Rito, and Rouleau proved that the weighted projective space 138 with weight 138 also is a complex crystallographic reflection group quotient. So, but in fact, this corresponds to the group K12 in the whatever it means in Popov classification, and this one is non-split. So this is not so surprising because the proof of Schwarzman and Tokunaga Yoshida concerns split case. So, to my knowledge, 2 groups has to be considered to finish the n is equal to 2 case. First of all, there is still one non-split case in Popov classification. And second, this group exhibited by Goryunov and Mann is split, but not dealt with anywhere so far. But okay, so to summarize, there are many works for n is equal to 2. All right, so another big family of groups that has been proved, for which Bernstein-Schwarzman conjecture has been proved, is crystallographic groups of Coxeter types. So let me explain this. So first of all, a crystallographic reflection group, so of course reflection groups, I mean by that generated by reflection, is of Coxeter type if the group of the linear part is conjugate to a finite subgroup of the orthogonal group ON. So in other words, it comes from real finite group. And now, using a combination of works of Loyenda, Bernstein, Schwarzman, Zenself, and Katz-Peterson, we have that the quotient of Cn by any irreducible such a group, so of Coxeter type, is a weighted projective space. So here the proof is complete. And here what is nice is that complex crystallographic Coxeter reflection groups are classified in terms of affine root system. And in this case, you can also describe easily the weight of the weighted projective space that appears in this theorem. Here, the weighted projective space in the theorem are in fact labels, the labels of the extended Dedekind diagram of the corresponding affine root system. So more precisely, if I consider the imaginary, positive imaginary roots theta minus alpha 0, so the positive imaginary roots that generate the set of positive imaginary roots, then the ki's are precisely the coefficients in the simple roots. So for example, for an, you find the weight are all 1. For E6, you have this weight and so on. So here it's very nice because you have a simple description of the weights, which is not the case for any crystallographic group. All right. So this is roughly what is known about this conjecture, and now I would like to explain that our result is a particular case of this conjecture.
Sorry. Can I ask you a question?
Yeah.
Is that so? On this slide, is that the only restrictions? Is it known to be the only restriction on the weight?
What is a restriction? Sorry.
The restriction you wrote down. You know, these are the label on the extended Dedekind diagram.
Yeah.
Are these the only restrictions in the Schwarzman-Bernstein conjecture? In other words, can I have arbitrary, for example, if I give you an arbitrary weight, K0 to the n, can that be realized as a quotient?
Yeah, I understand. Yes, because in fact there is a correspondence. So any affine root system give you crystallographic reflection groups. Then you can consider the corresponding quotient, and their result says that this is a projective space with the weight starting from your affine root system.
I see. So there are no.
So maybe I should. By the way, thank you for your question, because I should explain a little bit. Who did what. So actually Katz-Peterson consider all classical crystallographic Coxeter types. So this means all Coxeter reflection group associated with classical affine systems. So actually what they prove is that the algebra of invariant, I will explain a little bit their strategy later, is a polynomial using a theta function. And Bernstein and Schwarzman consider all case, but their proof needs to exclude DL for some reason. But together with Katz-Peterson, we have all cases. And for Loyenda, first of all, it was the first. He was the first, and he considered a subfamily of this family. So anyway, at the end, the proof is correct for all Coxeter reflection group. All right. So any other questions? All right. So now I would like to, as I mentioned, I would like to explain why it is a part of this conjecture, because as you remember, I consider a quotient of the Jacobian by the finite group. So in principle, it's not related. But now I notice that the action of the finite group G on the Jacobian gives rise to a complex crystallographic reflection groups as follows. Let's consider the period lattice of C. And so that J is just a quotient of C3 by this lattice. And now we notice that the quotient I consider in the main theorem is isomorphic to this quotient, where gamma is a split complex crystallographic reflection group. So here lambda identified with a subgroup of translations, and G is a linear part of this subgroup. And in fact, G appears in Popov classification of finite complex reflection group as G3 of 4. So here, this is a fragment of Popov classification And you see in the number 24 is our group. And it can be described in terms of some complex root system. And in the fourth column, you find it's not exactly our lattice, because our lattice is of rank 3, but it is a power 3 of this lattice, essentially. And 3 is the dimension of our vector space. So next, in Popov classification, now the group gamma, which is a real crystallographic group, is K24. And 24 refers as Shepard-Todd classification, which was done previously, but Popov classification is given in terms of graphs. So here, it's again a fragment of Popov classification, and our group appears in K24. Sorry, I should not move the mouse. So you see, so here you see really our lattice, because the fourth column gives you the subgroup of translation. And yeah, maybe I don't need to comment on the data. And the fact that the cocycle is 0 tells you that K24 is split. Okay, so now we notice that K24 is very special for several reasons. So first of all, here n is equal to 3, it acts on C3, and C3 is the smallest dimension for which nothing is known about Bernstein-Schwarzman conjecture for a genuinely complex reflection group, outside Coxeter types, I mean. And second, remember that G is a product of H with plus minus 1, and the Klein simple group is the only non-abelian simple group that can be embedded in a complex crystallographic reflection group for n is equal to 3. And thirdly, also what is special with K24 is that all crystallographic reflection group for n is equal to 3 are solvable except this K24. So again, our result proves the conjecture in these particular cases. So now I would like to discuss the strategy of the proof. So the first difficulty in this case, it has contrary to the Coxeter type, there is no natural way to describe the weight a priori. There is no anymore affine group system underlying our group. So the first problem is to find candidates for our weighting projective space. So what we did, in fact, is that we completely determined the singularity of the quotient. And in this way, we found candidate for the weight, and we conjecture the result I told you at the beginning. So this proof, and then we were able to prove, in fact, the conjecture. So the proof splits into several steps. So first, as I mentioned, we determined the singularities of the quotient. And then we showed that the quotient is isomorphic to a degree 8 hypersurface in a bigger weighted projective space of weight, 4-dimensional weighted projective space with weight 1, 1, 2, 4, 7. So why this is interesting? First of all, yeah, the main ingredient for that, I will explain this, but the main ingredient is the computation of Hilbert function of the invariant of the algebra of invariant of theta function on the Jacobian. So this part followed the strategy of previous people, so Bernstein, Schwarzman, and Katz-Peterson. And why this result is interesting? Because in fact, we notice that our weighted projective space also embeds into a bigger weighted projective space. So it's clear that it embeds. For instance, if you put the first coordinate to be 0, it's clear. But what is less clear is that it embeds into a degree 8 hypersurface, which is namely this hypersurface. And the embedding is given as follows. So I denote by x0, x1, x2, x3 the coordinate in P2, 4, 7. So the weight are 1, 2, 4, 7. And then I use this embedding, so I send to x0 square, x1, x2, x0, x3, etc. And you notice that the image give you something of weight 2, 2, 4, 8, 14. And obviously the image is exactly this hypersurface. But now it is well known that this weighted projective space is isomorphic to P11247 because you can divide by 2. So now we are happy because we have 2 degree 8 hypersurface in the same weighted projective space with the same singularities. And last step, we were very lucky because we were able to prove that the only octic in this 4-dimensional weighted projective space with the correct singularities is actually equivalent to this hypersurface. So this is the strategy. So let me explain the first part. So about the singularities. So as I already mentioned, the image of a point in the Jacobian is a non-singular point if and only if its stabilizer is generated by reflections. Otherwise, it is a singularity locally analytically equivalent to the linear quotient of C3 by this stabilizer. So then what we did is to compute all possible stabilizers in the Jacobian. So so in the theorem I would like to state now, I did not I use a standard notation. I did not by 1 over D and 1 and 2 and 3 the cyclic quotient singularities of C3 by the cyclic group of order D. Acting on C3 by its generators by multiplying these primitive roots of unity by the corresponding weight. So this is my notation, and the theorem is the following. So first of all, the quotient is a normal simply connected variety. So actually it's even strongly simply connected, which means that if you remove the singular locus, it's simply connected. So this first part is actually not due to us. It's a general result because gamma is generated by reflection. And the second part describes the singular locus. So the singular locus is is a union of 2 irreducible components. First, you have a projective line isomorphic to P1, and in this line, all but 1 points have the singularity of type 1 over 2, 0, 1, 0, 1 in my notation, but this means the Cartesian product of C by the Duval surface singularity of type A1. And there is a unique point in this line where the type of singularity is this one. And now there is also an isolated point, let's say P, whose singularity has analytic type 1 over 7, 1 to 4. And you see that this last singularity, when we saw this singularity, we thought about this weighted projective space because we can check in some affine chart that this type of singularity appears. And then we check it was indeed the same. And in fact, the weighted projective space P1247 is also strongly simply connected and have the same singularities of as J over G. So this is the first part. So this led us to conjecture the isomorphism. And now I would like to explain the Hilbert series and theta-functions tools. So to explain this, I would like to explain the general idea of Loyenda, Bernstein, Schwarzman, and Katz-Peterson. So the general idea was to consider the abelian variety of Cn over lambda. So maybe I should explain the notation. So let's remember the conjecture, and I consider Cn over a crystallographic group of Coxeter types. And this group has a subgroup of translation, and this is the lattice I consider here when I consider the abelian variety. And I consider this abelian variety as a proj of the graded algebra of global section in of a power of an ample line bundle, which is linearizable by the linear part of gamma. So G here is a finite group, which is a linear part of gamma, and you can write A as a proj of this algebra. And what they did, so now they consider the quotient, and this quotient is so a quotient of this abelian variety by G, and this is the proj of the G invariant part of this graded algebra. And if we are lucky, this algebra, G invariant graded algebra, is polynomial. And the section of the powers of L are represented by theta function for the lattice lambda. So using theta function, these people were able to prove that the G invariant polynomial algebra is a free polynomial algebra. And this implied that the corresponding projective, so in our case is just A over J, is a weighted projective space. So this is the strategy. So mimicking this strategy, we tried to do the same. So our approach is to mimicking this approach. So we introduce also theta functions for the lattice lambda that appears as a period lattice of the Klein's curve. And so that the theta mk is basis of the space of global section of an appropriate power of an appropriate line bundle on the Jacobian. So then we also can write J like this. And here the problem that we encountered is that L cannot be linearizable by the action of G. So this, I will explain maybe this part a bit later, but the problem is that here, using Iguza's transformation rules, we see that some half integers appears and makes that this is not possible. But however, the even powers are linearizable by G. So we have to work with the second Veronese subalgebra. So we still have that the quotient is a proj of the second invariant, so invariant of the second Veronese subalgebra. And here we were able to study this algebra. But here we cannot expect this graded algebra to be polynomial. So what we prove is an isomorphism between this graded algebra and the second Veronese algebra of our weighted projective space. So we have several complications, but still this strategy were efficient because thanks to that, first of all, it was a strong support in favor to the conjecture because the Hilbert series coincide. And second, we use this to embed both variety in a higher weighted projective space. Okay, so this is a strategy, and I would like to state something more precise. So computing computing the character of these representations. So this is a k⁻³ representation of G, this space of global section on the power of the appropriate line bundle. We computed the Hilbert function of the algebra. We computed the character and use scalar product with a trivial representation, and this gives you exactly the invariant part. So we were able to compute the Hilbert function, and this is the result. So the result itself is not so interesting, but I wanted to show you that this is quite explicit. But it is based, it's good and not good, because it's good because we were able to do explicit computation and use transformation rules of theta function to compute. But the bad news is that it's difficult to imagine to extend to other groups. So anyway, we were able to compute this, and we observed that this coincides with the Hilbert function of the second Veronese algebra of P1247. So how to show it's the same? So in fact, the Hilbert series of this weighted projective space is easy to compute. So you can also deduce a second Veronese subalgebra. So this is easy. And now how to compare? You compare the coefficients. And what is nice is that in fact there are some periodicity in this Hilbert series. And so it was enough to check only the first coefficients. I think it was until it was enough to go, I forgot, but maybe something like 42. I think the period is something like 14. And so it was enough to check finite numbers of coefficients. All right, so, okay, so now we have this, and I would like to explain how to use this to have more precise statements. So now I would like to explain how to embed this quotient as a degree 8 hypersurface. So what we prove is that there exist 5 G-invariant theta function of degree ki, so some degrees, but the ki are here 2, 2, 4, 8, 14. So this is exactly the double of the weight I mentioned before, such that associated sections generate the whole G-invariant algebra. And moreover, the ideal of relations between these generators is generated by a single relations of degree 16, and so the quotient is isomorphic to a degree 8 hypersurface. So the idea of the proof is the following. First, we found 4 algebraically independent functions, which are essentially G average of theta function with appropriate degree, so 2, 2, 4, 8. So this function generates a free polynomial algebra, let's say S prime. And then we compare the Hilbert function of this subalgebra and the big one. And okay, whatever the numbers, you notice that up to degree 6, so 0, 1, 2, 3, 4, 5, 6, they coincide. And after there are some discrepancies between the degrees. So this means that our phi generate S in degree, S is a G-invariant second Veronese algebra in degree at most 7. So we need one more generator up to degree 7. But now you see that the difference of dimension for degree 7, it's in red here, it's only 1. So let's say, let's keep phi 4, which of degree 7. And now we observe that there are only 37 monomials in these phi's. And in fact, more precisely, 35 involve only phi 0 up to phi 3. And there are 2, phi 0, 4 that I wrote above 36 and phi 1, 4 in degree 8. But you see that the difference between here and here, between 35 and 36, is only 1. So this means that there is only one linear relation Fi between the monomials phi 0 and phi 4 in degree 8. So unfortunately, we cannot say exactly what it is, but what we know is that there is one relation. And now it's not difficult to see that if I consider, if I write my weighted 4-dimensional weighted projective space as a proj of some of the graded algebra R, then the natural quotient given by our result is an isomorphism. And so we get the expected result that the quotient is isomorphic to the degree 8 hypersurface in this weighted projective space. All right, so the last part is we compare, we study degree 8 hypersurface with correct singularities. So let's consider any arbitrary hypersurface with correct singularity. So that is to say the same as P1247. And the aim is that it's automorphic to the right one. So the miracle is that there is only, indeed, up to analytic equivalence, only one. So, okay, I just explained briefly the strategy. You write F8 arbitrarily in terms of homogeneous coordinates, so that it's homogeneous of degree 8. And first of all, using that the singularity as those of P1247, we obtain that phi and A0 are non-zero, so the first two coefficients. And this is good because then we can use change of coordinates, and using change of coordinates, we notice that it's enough to assume that F8 has this form, which is close to the one we want. And then using again the singularities, we eliminate all cases except the case where all BI are zero. So this concludes the proof because we have the expected hypersurface. All right, so this is what I wanted to explain, and I just wanted to say that there is our variety, our quotient is not Calabi-Yau, but there is a related Calabi-Yau variety. If you consider instead of the quotient by G, you consider the simple Klein's group H, then the quotient is a Calabi-Yau variety, which looks interesting. In fact, we can show that it admits a Crépin resolution, and we can compute several invariants like a Euler number or several other things. And we would like to study now this Calabi-Yau variety. For instance, can we compute the mirror of this variety? Is there a chiral counterpart of this variety? So I didn't write anything so precise because it's a current joint project with, again, Dimitri Markouchevitch, but also Dan Israel, who is a physicist. So we hope to continue in this direction with more physics applications. Okay, and I think I stop here. Thank you very much.